Yay, parabolas!
Is that my good cream?
Nope! You've seen this curve 1,000 times. In every jump, every throw, every knockback. It's hidden in plain sight. In this video, you'll see how parabolas are used in video games, and no, they're not just for falling objects. Although they mostly are. So, parabolas. We all know them as the functions that are either happy or sad. When we look at them, we usually see a smile or a frown. But that's just our human brain in action. When a game designer looks at parabolas, they actually see boobs. They see an object throw trajectory or a character's jump arc. Imagine that your character is at the origin throwing an object at an angle. This plot is its trajectory. Or think about a character jumping forward. Again, this is its trajectory. But what does this function have to do with how objects behave in midair? And how do game designers calculate its parameters to get the right angle and speed every time? Stick around and let's find out. To see how the parabola manifests itself in this case, we need to first take a look at its definition. By definition, a parabola is a function that satisfies this condition. And just so we can get a feel for how it works, because that's what this channel is all about, let's look at its graph. When we play with the parameters, we can see that the A parameter changes how concave or convex the function is, which kind of looks like it controls the strength of gravity, but not quite. The B parameter has an effect that looks like it's controlling the throw speed of the object, but again, not quite. And the C parameter is the same offset value we discussed in the linear function video that increases or decreases the Y directly. If you remember the last video, we showed some examples of this parameter being ignored or zeroed. This, unfortunately for it, is a recurring theme in physical mathematics. So, we've seen that the parabola parameters are close to representing real physical properties like gravity and initial velocity, but not exactly. Let's show how a real throwing trajectory looks like. Okay, don't panic. I know it looks like a lot, but what's relevant for our purposes is only understanding this conceptually. Although for those of you who are interested, I'll show how it's derived at the end of the video. Anyway, for now, all we need to understand is that alpha, which is this Greek letter, is the object's throwing angle, v is the initial speed we give it, and g is the gravity constant, which determines how much the ground attracts the object. If we plug this equation into our graphic calculator, you can see very clearly how it all starts to make a lot of sense. You can now see how changing each factor shapes the trajectory in a very sensible manner. In this equation, alpha actually controls the angle at which the object is thrown, v controls the initial speed, and g controls the gravity. Now, I'm guessing some of you can already see why this is showing up in a video about parabolas. Can you see the parabola in this equation? Here it is. You can see that once again the offset parameter is ignored, although if we want we can add it in and see that what it does is increase our initial thrown height. The important thing to remember is that this plot shows how the object travels, and we can see that its path is determined by the A and B parameters, which in turn are dependent on the three basic parameters of this motion, which are angle, speed, and gravity. This, by the way, is the same case when our player jumps or gets knocked back. Same equation, same physics, only different parameter values. So, now that we understand this, we know that when a developer wants to show us the projected trajectory of our shot, all they need to do is check what angle we are currently aiming at, while knowing the speed that will be given to this object, and the gravity constant of the game. Plug it all into this equation, and voila! What's even more mind-blowing is that the game engine, this is what's doing all the physics calculation in the background, does not use this equation at all, and still arrives at the same result. Game engines use what's called numeric calculations. This type of calculation, which I'll explain in detail in a separate video, is an aggregate calculation, where you start at an initial condition and calculate the accumulative change of every time step individually. You can think of every time step as being a single frame in the game, although it is usually not the same rate. Compare this type of calculation to our equation, and you see that by using the parabola, we get the entire trajectory right away, much cleaner and faster. So why don't engines use this equation rather than the numerical calculation? Write down your thoughts in the comments and I'll show the answer in the next video. Back to parabolas. We've shown how thrown object trajectories can be predicted using parabolas, but this application is not just for falling objects. Another form of application of parabolas in video games is in UI stacking. Many games use curved UI elements to either make it look like it's viewed from within a helmet, or to simply look cool. You can see clearly in the Halo games, where the UI elements are positioned along the parabola with a very large A parameter. Another way games use this function in UI is when we're collecting items or coins. When designers want their games to visualize the items traveling into the player's purse, many times they won't shoot them directly into the character's purse, but rather choose a parabolic path, which makes it look much more natural and satisfying. How developers do this is fairly simple using parabolas. Remember our graph from earlier? All we need is to specify how high the item's apex should be and calculate its distance from the player, and from that we can calculate the parabola's A and B parameters. We determine the item's horizontal velocity and update the vertical component according to this parabolic equation. And don't sweat how I derived this equation. While I believe math is interesting, some derivations are just plain boring, so I'll save you that one. You're welcome. Now for the derivation of the equation I promised earlier, for those who are interested in seeing how the parabola emerges from the physics. I'll try to make it short and sweet. The object is thrown at an angle and therefore has a velocity in the horizontal direction and the vertical direction. The velocity in the x and y directions depend on how strong we threw the object, which we call capital V, and on the angle alpha that we throw it at. The dependence looks like this. Now don't freak out about the trigonometry here. The sine and cosine functions only say how much of the velocity v is in the x direction and how much of it is in the y direction. That's it. And that's of course based on the value of alpha. Okay, so on the x-axis, the thrown object does not experience any forces, so its velocity is constant. So its location along the x-axis looks like this. On the y-axis, the object experiences a downward force, that is gravity, and so it accelerates down at a steady pace. The kinematic equation for an object in steady acceleration is this one. In our case, the acceleration a is equal negative g. It's negative because the acceleration points downwards, and g for gravity. Maybe I'll show how this equation is derived in a later video, but we'll see about that. Anyway, you can already see the parabola emerging on the y-axis. The only thing that's left is to substitute the t values, because we want to see the full height and length plot and not how the height changes with time. From the x-axis equation, we can see that t is equal to x divided by vx, and plug in that in the y-axis equation, we get this. Now, if we also plug the values for the x and y velocities we've shown earlier, and clean the equation a bit, we get the equation I shown earlier. This one has the extra y0 offset, which if you remember increases the height of our parabola. If you want to simulate something being thrown from a height, you can plug that height for the y0 and give that offset value some respect. Okay, so that's all there is to parabolas in video games. You can see that by adding another element to our original linear function, we can get a more complex reaction that can simulate real-world scenarios and even some nice curves for UIs. In the next video, we'll talk about the inner workings of all game engines, numerical operators. We'll learn how game engines calculate where objects should move towards, how collisions are calculated, and much more cool stuff using numerical integration and derivation. As always, if you enjoyed this video or found it interesting, please consider leaving a like, comment, and sharing it. And of course, subscribe to this channel and join our lab if you also think that the offset parameter deserves better. Thank you all for watching, and I'll see you in the next one. Cheers, guys!